Hello, and welcome to this Fluid Components International, or FCI, webinar. Now I would like to introduce today's presenter. With us today is Brian Lawson. Brian is the Regional Sales Manager with FCI. To read more about Brian today, just go ahead and look at that speaker bio window right next to the main presentation window. So Brian, welcome to today's event. And with that, I'd like to pass things along to you to get us started. So go right ahead.
Thanks, Katie. Before we get started, I'd like to thank everyone for setting aside some time to join this presentation. Without further delay, let's get started. Gas flow measurement and functional safety on the pathway to net zero. Before we dive in, let me introduce myself. My name is Brian Lawson. I'm the Western Regional Sales Manager at FCI. I have over 28 years of experience in instrumentation and control in the Rocky Mountain region. During that time, I have focused on flow, level, pressure, temperature, and analytical measurements. In addition to my own industry experience during this presentation, I also use the knowledge from 6 decades of experience that FCI has in hydrogen measurement. Before we get started today, let's quickly talk through the agenda. First, we will look at why hydrogen. We'll look at many of the drivers behind it. We will review the hydrogen value chain. We will look at forms of green hydrogen production. We will address some of the challenges and considerations when measuring hydrogen. We will review some green hydrogen applications, and then we'll look at the safety and functionality that exist in the system. So what is net zero? Net zero refers to the state where emissions of greenhouse gases due to our activities and the removal of those gases are in balance over a given period. That simply means we are removing as much or more of greenhouse gases than we create as an industrialized civilization. Why is this important? It's important because we need to limit climate change and preserve our planet. We need to limit global temperature increases to 1.5 degrees above pre-industrial levels for a healthy ecosystem. Currently, the Earth is already about 1.1 degrees warmer than it was in the late 1800s, and emissions continue to rise. To limit this rise, an international climate change treaty called the Paris Agreement was signed in 2016. It calls for emissions to be reduced by 45% by the year 2030 and reach net zero by the year 2050. How can this be achieved? Moving to a net zero world is a challenge. It calls for a complete change in how we produce, consume, and move about. The energy sector is a source of around 3/4 of greenhouse gas emissions today and holds the key to averting the effects of climate change. Replacing coal, gas, and oil-fired power with energy from renewable sources such as wind and solar would dramatically reduce our carbon emissions. What is being done? Globally, a growing coalition of countries, cities, and businesses have pledged to get to net zero emissions by the year 2050. Over 140 countries, including our biggest polluters, China, the United States, India, and the European Union have all set net zero targets, converting about 88% of global emissions. In addition, more than 14,000 companies, thousands of cities, as well as thousands of educational institutions, and over 600 financial institutions have joined the Race to Zero. The Race to Zero is a pledge to take immediate action to reduce global emissions in half by the year 2030. As of today, the combustion of fossil fuels contribute to about 83% of CO2 emissions. In the process of decarbonization, addressing transportation and our building infrastructure, the 2 largest producers of CO2 at nearly 60%, will be the key. Is there a viable alternative to fossil fuels? Industry says yes. Enter hydrogen. Per the McKinsey analysis, hydrogen on its own could contribute to over a 20% reduction in greenhouse gas emissions globally by the year 2050. Currently, there are around 1,000 hydrogen project proposals announced globally. Only 795 of those target the year 2030 for full or partial deployment. It is also projected that $320 billion of investment into hydrogen projects will be added by the year 2030. Currently, only $29 billion have passed the final investment stage. Experts estimate 38 million tons of hydrogen will be available for use by the year 2030. As of today, less than 1 ton is deployed. With all that being said, we will be seeing a lot more hydrogen applications moving forward. Let's take a quick look at the hydrogen color spectrum. The color spectrum is a tool used to classify and identify different types of hydrogen based on production methods. For example, green hydrogen, produced using renewable energy sources like solar or wind power through electrolysis, considered the most environmentally friendly option. It will also be where we're focused most of our time today. Blue hydrogen, it's derived from natural gas with carbon capture and subterranean storage technology to mitigate those emissions. And finally, black hydrogen, produced from coal without carbon capture, resulting in extremely high greenhouse gas emissions. Not very preferable where we're headed now. Let's quickly talk through the hydrogen value chain. This covers the process from producing to utilization of hydrogen as an energy source. First, let's talk about how hydrogen is produced. In general, hydrogen production is classified into two categories: high carbon and low carbon production. High carbon includes gasification, using coal or organic material to generate hydrogen, steam reforming, currently the most common method of hydrogen production because of the cost. This method heats natural gas with steam to produce hydrogen, but left untreated, releases high amounts of carbon dioxide. If paired with carbon capture, steam reforming is also considered a low carbon source. Electrolysis is another low carbon production method, using electricity to split water into hydrogen and oxygen. When paired with renewable energy sources, electrolysis is a net zero process. Even with its high costs, it makes it more desirable. Today, the hydrogen supply is over 99% high carbon production. There are four common types of storage. The first, compressed gas storage. Hydrogen stored over at 5,000 psi, probably the most common. Second is cryogenic storage in liquid form, low pressure and much more stable to transport, but uses a lot of energy in its production. Metal hydride storage is another option, but is less common due to cost. And finally, chemical storage, where hydrogen is transformed into chemicals such as ammonia, but once it reaches its destination, it must be cracked for usage. Once stored, hydrogen needs to be transported to its use location for distribution. Common methods are supplied through pipelines, truck transport to small storage sites for remote distribution, ship transport, typically done in liquid form over long distances. Hydrogen can be utilized in many applications. Some common uses include transportation, fuel cells for electric power cars, buses, and other mobile equipment, energy and heat production for the grid power, and various industrial applications requiring cooling, heat, and power. Lastly, hydrogen can be stored during times of high renewable energy production, such as bright sunny days, and then be converted back to electricity when supply is at its lowest, for instance, nighttime or a cloudy day. As we insist on becoming more climate friendly, hydrogen will increase around the globe. It will play a key role in meeting the challenges of decarbonization and advancing the efforts towards net zero. Green hydrogen is a system where hydrogen is produced through electrolysis, using electricity solely from renewable energy sources like solar or wind, resulting in zero carbon emissions, and then utilized in various applications like transportation, industry, or energy storage, effectively replacing fossil fuels with a clean energy source. The key aspects include the electrolysis process, powered by renewable energy sources, hydrogen storage, and its use in applications in fuel cells or combustible engines to generate power or heat for various processes. The process of producing green hydrogen is through electrolysis, using a renewable energy source such as wind, hydro, or solar. Simply put, using electricity to split water into hydrogen and oxygen gas. There are three common types of electrolyzers. The first, the PEM electrolyzer. It contains a proton exchange membrane that uses a solid polymer electrolyte. When an electrical current is applied to its cell stack during water electrolysis, the water splits into hydrogen and oxygen. Hydrogen protons pass through the membrane to form H2 on the cathode side. The next is the alkaline electrolyzer. It contains water and a liquid electrolyte solution such as potassium hydroxide or sodium hydroxide. When a current is applied to the alkaline cell stack, the hydroxide ions move through the electrolyte solution from the cathode to the anode of each cell. The hydrogen gas bubbles are generated at the cathode and the oxygen gas is generated at the anode. Solid oxide electrolyzers. Solid oxide electrolyzers are solid oxide electrolysis cells that run in regenerative mode. They use a solid oxide or ceramic electrolyte. When current is applied and water is fed into the cathode, the water converts into hydrogen gas and oxide ions. While the hydrogen gas is captured for purification, the oxide ions move to the anode and release electrons to an external circuit to become oxygen gas. Each technology has its strong points and are selected for various reasons. For instance, PEM electrolyzers run at lower temperatures, and loads can be easily varied for fluctuating power sources. AELs are highly efficient and tolerate subtle load changes. SOEC run at high temperatures and will not tolerate load changes, but SOEC cells can be used in reverse as fuel cells to generate power. For purposes of our discussion today, we will be focusing on PEM and AEL electrolyzers. What does any of this have to do with process instrumentation and thermal flow meters? Well, as more production capacity is added, there is going to be a greater need for gas analyzers, pressure, temperature, level, and flow instrumentation. Therefore, it is going to be important to understand the different measurement technologies available for hydrogen gas and the advantages and disadvantages of each. Today, let's discuss thermal dispersion technology flow measurement. First, let's discuss the construction of the thermal dispersion sensor. This graphic shows the basic construction of a sensor that consists of a sensor tube with two thermal wells welded to the end. The first thermal well, referred to as the active sensor, contains a PT1000 temperature sensor plus a heater element inside. The second thermal well, referred to as the reference sensor, contains only a PT1000 temperature sensor. The heater element is supplied with a constant power from the electronics and creates a differential temperature between the active and the reference sensor in process. In addition to supplying the power to the heater, the electronics also senses the temperature difference between the active and the reference sensor. As the process moves through the piping, the molecules of the process cool the active sensor, changing the differential temperature between the active and the reference sensor. This change is directly proportional to the mass flow of the process. Simply put, the differential temperature measured at the sensor is directly proportional to the actual density of the gas multiplied by the actual velocity of the gas. That, multiplied by the area of the pipe, provides a mass flow of the gas and can be displayed in your choice of engineering units. Since thermal dispersion sensors are a direct mass flow measuring device, not volumetric, changes in temperature and pressure directly affect the density of the gas and are automatically corrected for, providing a stable mass flow reading regardless of those fluctuations. Before we get into applications, let's discuss best practices for hydrogen measurement. Although PEM electrolyzers and green hydrogen are new in the grand scheme of gas flow measurement, challenges and best practices in hydrogen measurement are not. Over the past 30 years, FCI has calibrated and successfully deployed many thousands of instruments into hydrogen applications. This graph shows the performance of a thermal flow meter using air equivalency calibration method, then tested in actual gas conditions. Other than 100% nitrogen, you cannot lay the curve for any of the other gases on top of the black air curve and expect linearity across the entire flow range using a K-factor adjustment. You'll also start seeing limitations on low or high flow capability depending upon the gas being measured. This helps show the best performance is achieved when you calibrate with actual process gas under known process conditions. Often overlooked is the use of inferred variables in flow measurement. This is when a density is assumed without the meter technology being tested on a traceable calibration stand. To save costs, an air calibration might be performed with a linear correction factor applied to offset the differences in gas densities. Depending upon the technology, these equivalencies don't necessarily account for all the thermophysical properties of hydrogen, such as absolute viscosity, specific heat, and thermal conductivity. Changing process conditions are not always accounted for when a density is assumed, leading to an incorrect measurement of the actual mass of gas being measured. Per ISO 14511, it confirms that the best practices for calibration of a flow meter is to utilize actual gas and mirror the process conditions being measured. Hydrogen calibration adds cost, yes, but they should be easily offset by the added confidence in your readings being accurate and reliable. Let's look at some factors that illustrate why an air equivalency calibration for hydrogen flow is not a good practice. The differences in thermophysical properties of the two gases are extreme. If using a linear correction factor, the results will be highly questionable given the equivalent flow of hydrogen is only 4.5% that of air. Not only does this type of correction impact flow meter performance, it also greatly limits the measurable flow range. Even using a hydrocarbon such as natural gas for an equivalency media is not much better. That correction factor is still under 10%. This is just more confirmation that using hydrogen for calibration media is necessary to ensure the best performance of your flow meter. Many applications don't require custody level accuracy, so why unnecessarily pay for that level of performance? The typical accuracy of a thermometer is plus or minus 1% of reading with a repeatability of 0.5%. This level of performance has proven to be suitable for many applications in process industry, with the added benefit of a lower total cost of ownership. Regardless of the technology, published accuracy is based on ideal conditions. When calibrated at the factory, ideal straight runs ensure that velocity profiles are fully developed. Often these ideal conditions are hard to come by in the field, especially in larger line sizes. Elbows, valves, and other obstructions within the meter run will result in a distorted velocity profile. Be sure to work with a knowledgeable manufacturer that can help you better understand the impact of the meter accuracy under actual flow conditions. Most flow measurement technologies have issues when a gas flow transitions between laminar and turbulent flow. For thermometers, this most often can be seen in smaller line sizes. Since the flow is neither laminar nor turbulent in this region, there are calibration challenges associated with the randomness of the velocity profile. This graph is to help visualize how transitional flow can impact thermal flow measurements. The blue curve shows a signal from a thermal sensor when the flow passes through that transitional zone. The result is a noticeable fishhook in the output. When unaccounted for, linearization of the analog output could introduce an error of plus or minus 10%. Ideally, we want our sensors to be smooth as shown by the purple curve. One way to eliminate transitional errors is to restrict calibrations to either laminar or turbulent flows. This would greatly reduce the turndown ratio when trying to measure very small mass flow rates. However, some available instruments utilize tab-type flow conditioners that create vortices to eliminate error associated with transitional flow and provide a linear output across a larger flow range. Let's talk about several safety considerations that come into play when handling hydrogen. For instance, hydrogen has a wide ignition range of 4 to 74% in the presence of air. It has a flame velocity of 5.6 feet per second, which is 4.25 times faster than natural gas. Since its combustion is nearly invisible, open flames are not easily noticeable and can lead to accidental burns. Hydrogen takes low ignition energy. Hydrogen is stored at pressure ranges from 5 to 10,000 psig, and since hydrogen is colorless and odorless, leak detection and proper ventilation is required when stored in enclosed spaces. Also, the small molecule size can cause hydrogen embrittlement of metal pipes, resulting in the possibility of malformation of the pipe and pinhole leaks. For market segments such as oil and gas, chemical and refining, it is common for instruments to be installed in Class 1, Div 1, and Div 2 hazardous areas. As such, it is important to select an instrument suitable for these environments. You'll want to confirm with the vendor that the product they are offering has the appropriate third-party approvals for that application. Another item of interest within the process industries is functional safety. This might further limit your options when looking at suitable technologies. You'll want to verify with your vendors that their product offering has the appropriate pedigree. Without items such as failure rate data, preferably verified by an authorized third party, we will be unable to perform suitable analysis of our safety instrumented function that accounts for the logic server, final element, and sensor. Safe failure fractions and safety integrity levels alone, without knowing other hardware architecture constraints and actual failure rate data, is not enough to be thorough. Now let's take a few minutes and look at some critical points of measurement in the hydrogen electrolysis process. On this slide, we are looking at a PEM electrolyzer connected to a wind farm. It is utilizing excess energy not used by the grid to supply power to the PEM and produce hydrogen for storage and later use. There are two key points that need to be measured and maintain the functional safety of this process. The first is verifying the flow of water into the system. Water is crucial because without water, there is no molecular split and no hydrogen production. In addition, the lack of water could result in residual current in the process, causing overheating and degradation of the electrodes. With a reliable flow switch in place, a system shutdown could be initiated to prevent damage and the possibility of a catastrophic failure. The second is air ventilation monitoring of the PEM enclosure. This is critical because we need to ensure that any residual hydrogen that may be released into the enclosure is dispersed before accumulating and reaching its flammable limit. Since the presence of hydrogen is colorless and odorless, strict ventilation standards are in practice to make sure it is quickly diluted with air, minimizing the risk of ignition. In this case, FCI utilizes the FS10 family of products. With our SIL2 compliance, the product allows confidence. Another application is nitrogen purging. Nitrogen purging is done with electrolyzers in hydrogen production systems to remove residual oxygen and other unwanted gases from the system before, during, and after electrolysis, ensuring safety and preventing potential explosions by creating an inert environment with nitrogen, which is a non-reactive and displaces gases like hydrogen, oxygen, and also remove other contaminants that could corrode or degrade system components. This is specifically important when starting up, shutting down, or during system maintenance of an electrolyzer. The amount of nitrogen purged into the system is measured to ensure the entire system is saturated and ready for safe operation. Or in cases of system maintenance, safe for an operator to perform his duties under safe conditions. This again is a great opportunity for the FS10I product from FCI. The SIL2 compliance with this instrument lends itself well to ensure the operator is maintaining functional safety. Another critical area to measure is in the storage area. When hydrogen is stored inside, just like air ventilation on the electrolyzer enclosures, storage areas also need to have ventilation monitoring for the same reasons. Avoid buildup of residual hydrogen in the area and preventing the levels reaching their LELs, ensuring operational safety. This is another great application for the FCI FS10I. In the previous two slides, I was specifically addressing PEM electrolyzers. Shifting gears a bit, I want to address an application unique to alkaline analyzers. A critical measurement to maintain functional safety of the system is flow monitoring to the analyte and catholyte systems. Optimal performance of an AEL electrolyzer relies on maintaining balanced flow between those two circuits. Flow switches in these circuits ensure pumps are working efficiently and allowing optimization of process efficiency. They also prevent overpressure or flooding, which would cause operator safety hazards and possible system failures. For this application, FCI uses our FLT93S flow switch with SIL2 compliance to maintain functional safety of their system. The final application I'd like to discuss is flow monitoring into hydrogen and oxygen analyzers. Measuring the gas output of the electrolyzer allows the operator to have a performance and efficiency assessment of the electrolyzer itself. Sample lines pull off sample to an analyzer such as a Michel Instruments H2 or O2 analyzer and provide a detailed analysis of the stream content. This is an important measurement since many signs of process upset will result in unbalanced yields of H2 and O2, as well as provide early indicators of issues in the overall electrolyzer operation. Monitoring flow in both the hydrogen and oxygen sample lines ensures you are reading real-time process data. For instance, without flow monitoring, and for some reason one of those sample lines became plugged, you could be analyzing the same sample repeatedly. This would not provide the data needed for the operator to make critical process adjustments to ensure the electrolyzer is operating at its highest efficiency level and ensuring the high level of functional safety in this application. In this application, FCI would use an FS10A flow switch specifically designed for small line analyzer applications to ensure that we have continuous sample flow to the analyzer. That concludes our presentation. I hope you found some of the information useful. If you would like more information after the webinar or would like to discuss flow switches or gas flow meter application, don't hesitate to reach out to us or contact your local FCI representative. Thanks again for your valuable time. I hope you have a great day. Thanks.
All right, Brian. Thank you so much for that great presentation. So we are going to move into our live Q&A session at this time. All right, Brian. So we're going to move into our first question today. So grabbing the first one out of our queue, what do you believe are the main challenges in scaling up green hydrogen production?
Yeah, that's a great question. I think really the main challenges are just initially there's a high production cost associated with green hydrogen. Typically we're using the high carbon style production for hydrogen right now at a lot of our factories and facilities. So the cost of that production is much higher than it is there. And then secondly, there's really a lack of infrastructure on storage and transportation right now. We don't have the pipelines, we don't have the fueling stations available for vehicle fueling, that kind of thing. And then just the need for renewable energy sources, hydrogen. The cars out there driving around in that just it doesn't exist currently, but it will continue to build.
All right, thank you so much for that first answer. All right, our next one here, you mentioned carbon capture and storage. How is this done and where is it stored?
Oh my goodness, that's a question that can be in a whole presentation topic itself. So essentially, there are basically four ways of capturing carbon with any of these applications. There's a post-combustion capture. It's the most common method we use, where we separate the CO2 from flue gases in like power plants and such. There is pre-combustion capture, and this method involves converting fuel into a mixture of hydrogen and CO2 before combustion, and it allows for much easier capture of the CO2. There's also oxy-fuel combustion. It's a method where the fuel is burned in pure oxygen, resulting in a flue gas that is almost entirely CO2, so it's captured. And then there's a direct air capture. It removes CO2 from the atmosphere using chemical absorption processes. All of them very effective. Like I said, the post-combustion capture is probably the most common used. From a storage standpoint, really right now there's three ways that are being used and utilized very regularly. So there's what they refer to as geological storage. It's the process where they actually pump that CO2 underground. They pump it into aquifers, depleted oil and gas reserves, coal seams that are unminable, and it holds the CO2. They also do ocean storage, where they inject the CO2 directly into the ocean at some pretty great depths. There's been some concern about this method, although not proven and not a lot of research done on it, but they just are not sure how it's going to affect the marine ecosystem. The other method is biological sequestration. So essentially it's using a process like the natural growth of plants to absorb that carbon dioxide and store it in soil. This is becoming a more common thing for power. We have a lot of power plants out there that are actually feeding greenhouses and whatnot and they use that temperature of the flue gas to control the temperature in the greenhouse. And they also rely on those plants absorbing that CO2. So in a nutshell, that's basically the carbon storage and capture methodology being used today.
All right, Brian, thank you so much for that answer. For our audience members, again, feel free to enter questions into that window, clicking submit, and we'll get through as many as we can today. If you don't hear your question, don't worry. We'll reach out to you following today. All right, next one here. What makes hydrogen so difficult to measure?
Hydrogen is difficult to measure just because of its physical properties, right? It's a very light gas. It has a very low density. it has very low Reynolds numbers. So when you're trying to use some traditional measuring, meters like turbines or differential pressure devices, that low density of that gas becomes problematic. And then because of those low Reynolds numbers, meters like a Vortex are very limited in what they can measure, because very difficult in that transitional phase in those Reynolds numbers to be able to get an accurate measurement. It makes thermal dispersion much more effective in those applications because, number one, we don't require, we don't care about that low density. One thing I will say, though, when using a thermometer, you need to be sure that it is calibrated in hydrogen gas for the application.
All right. Thank you so much for that answer. Moving on in the queue here. This person is asking, in the presentation, you mostly spoke about switches. Does FCI offer mass flow meters for hydrogen applications?
Yeah, the short answer is we absolutely do. We have multiple products that measure hydrogen very well. I stuck with switches during the presentation just because those are the critical safety points that we're currently doing in the electrolysis process. But if you guys have applications you're thinking about or whatever, feel free to reach out to FCI or an FCI rep. We'd be more than happy to talk to you about your process and recommend the appropriate meter for that application.
All right, great. Thank you so much, Brian. All right, this attendee is saying, is this instrument able to measure H2 flow rate in case that H2 is saturated in water?
Absolutely. So saturated gas is a difficult thing to measure, just for the simple fact that water itself has a really high thermal conductivity rate, and it causes problems with most sensors. So we have a specific sensor. We have a wet gas sensor that's specifically designed for really wet applications. What it does is it has a little screen filter media that it forces the gas across, and as it's passing through that filter media, it drops out that high liquid content and then flows the gas across those sensors. Definitely, we can make those measurements.
All right, great. Thank you so much, Brian. So this next question here. Will higher pressures in the flow rate compromise the accuracy of the measurements?
As long as you're staying within the guidelines that were laid out and the sensor was calibrated for, it should not cause any problems at all. As you know, we calibrate all of our meters in real gas applications with the real gas. So that allows us to have a much wider flow range and allow accuracy across that.
Great. Thank you so much for that answer. So next question in our queue here. Do both thermal flow switches and mass flow meters use the same technology?
That's a great question. So the short answer is yes. They use the same technology from the sensor perspective. The difference is how the electronics paired with that process that data and create a signal. So, but as far as the sensor itself goes, yes, we use the exact same technology. There is no difference. It's just, discrete outputs versus, your analog or your digital protocol that you're using to indicate your flow.
Right. Next one here, Brian. Do thermal mass flow meters have minimum piping requirements?
Absolutely. Like most flow technologies, there are minimum requirements that we have. Ideally, at the factory, we calibrate in what we call the perfect flow stream. So it's 20 diameters up and 10 diameters down.
That's our recommendations. Different manufacturers have different recommendations. So those do exist. However, I know that sometimes when you're installing a meter in the field in those kind of applications, those ideal flow conditions don't often exist. So in those cases, what we would use is a flow conditioner prior to our meter. That would change those requirements to a 3 up and 3 down from that flow conditioner. And, for your best accuracy when you're doing that, we also do recommend that if you're going to use flow conditioning, that the meter itself be calibrated with that line meter in the same flow line during the calibration process on your actual gas.
All right, great. Thank you so much for that answer, Brian. So again, if you have a question today using that Q&A window, enter it in, hit submit. We have a ton of questions in the queue here, so thank you everyone for all these great questions. But that means we will be answering a lot of these offline after the webinar is over today. So keep them coming. And if you don't hear your question being answered, do not worry. All right, Brian, next one here on the list. Are there concerns using a heated sensor with hydrogen since it is highly flammable?
Yeah, not at all. We've been doing these types of measurements in highly flammable gases and those types of applications for years. The thermal transfer rate is so small that there are absolutely no concerns using it in a hydrogen line.
Great, thank you so much. All right, next one in the queue here. Are all thermal manufacturers able to calibrate meters in hydrogen gas?
Boy, great question. I can only speak to the capabilities of FCI, but we do have a state-of-the-art Cal Lab in our facility, and we are able to calibrate those meters in hydrogen gas at your process conditions. So that probably have to be a question that would be directed to the individual manufacturers. I know some of them some of them have those capabilities, some of them outsource those capabilities, and some simply just use an air equivalency calibration. My recommendation, right, ask those questions and get those answers from those manufacturers.
Thank you so much for that. All right, next one here. What kind of questions do I need to ask a manufacturer to make sure my meter is accurately calibrated for hydrogen?
Boy, that's another great question. There's a lot that's involved with that. First of all, I think upon the initial issuance of a quotation for an application, you need to ask what tool they used to do the calculations to make sure that the meter's properly applied for the application. And then beyond that, ask a little bit about their calibration process. Are they using, traceability standards in their Cal Lab, such as NIST? Ask about what ranges and flow rates they're able to test at. And then, be sure you have the full understanding. And then once that meter is calibrated, are they supplying certified calibration documentation along with it? Those are really the key points to be concerned about.
All right, thank you so much for that answer. So we're going to take a couple more questions today. And then, as I mentioned, we're going to do most of our answering offline. So if you do have any other questions for Brian today, we are going to wrap things up in a couple minutes. So feel free to enter those in now so that we have them to answer following today's webinar. There's also some items listed right in your resource widget there, just below Brian's bio. You can grab those items as we're doing our Q&A today and take them with you today. All right, Brian, so a couple more before we wrap things up. If my process has times in which the hydrogen will contain some nitrogen, how will it impact the meter readings?
Wow, another great question. So if your hydrogen process occasionally contains nitrogen, it will cause small inaccuracies in the mass flow measurement. it depends on a lot of factors, right? How much nitrogen is present. You know, if there's a high percentage of nitrogen present, yeah, you're going to see some inaccuracies. But because of nitrogen and hydrogen are so far apart on that the heat conductivity spectrum, the presence of nitrogen, although it does affect, it has limited effect at small percentages.
All right, thank you so much, Brian. So this one here, can meters be installed in horizontal and vertical pipe runs? Are there any restrictions?
Yeah, yes, we can install meters in both, horizontal and vertical pipe runs. As with most meters, there's going to be, best practices that need to be followed in those installations. I would suggest, talking to the manufacturer about what those are, but the short answer is yes, we can do it in both horizontal and vertical pipe runs.
All right, thank you so much for that answer. So I'm just looking in our queue here, Brian. We do have a bunch of other questions coming in. So again, thank you to the audience. We are going to start to wrap things up right now. We do have so many questions that we will not be able to get to them. So thank you, everybody, for your participation. We'll get back to you after the webinar is over the next couple days. I want to say a huge thank you to Brian for an amazing webinar and for answering so many of our attendees' questions. So Brian, thank you so much for being here.
You're welcome.
Again, thank you all for taking time to attend this webinar event and for all of your great questions. Take care, and we will speak with all of you soon.